Let's compute another double integral. Just like in Calculus 2 and even in Calculus 1, we found that single integrals were very useful for computing areas. Analogously, double integrals are very useful for computing volumes of solids. So we just need some hypotheses to do this. So let's assume that we have a non-negative function where x and y is contained in some region in the plane. And so now we're going to define a volume of the solid as follows. We'll say the volume bounded above by f and below by the region r is given by this double integral, where we actually integrate the non-negative function f over the region r. And again, dA just represents the element of our area, and it could be dx dy or dy dx depending on how r is represented. So this is what we define to be the volume of the solid as we have it written here. Now let's just go ahead and use this formula and for a particular f. So now we have f of xy is equal to 4 minus y squared. We see that the x is free, so this is just a cylinder, a parabolic cylinder. And we have this triangular area for r. That is, y runs from 0 to 2 and x runs from 0 to y. And again, on this particular region, the function is non-negative. And so we use our definition, the volume of the solid bounded by f in the region will be given as follows. We write the iterated integral, that is y runs from 0 to 2, x runs from 0 to y, and the function is 4 minus y squared. Now, of course, this is a very simple function. It's just a polynomial in y, so it's not very difficult to integrate. So the first integration is with respect to x. So again, we just get a 4x minus an xy squared. And then we use the fundamental theorem to evaluate the antiderivative at y and 0. Notice evaluation at 0 gives us nothing but 0, but at y we get a 4y and we get a y cubed. That is, we replace x with y. Always make sure that you're replacing the correct variable, and that means that you're taking account as to which variable you used in the integration process. So now we've got a very simple antiderivative to do with respect to y. So now again, we add 1 divided by the new power, but with the 2 in the denominator, that will absorb one of the 2's here in this 4 to give us 2y squared. And of course here, we just get a y to the 4th divided by 4. And then we want to use the fundamental theorem, evaluate at 2 and 0. Again, evaluation at 0 will zero out the antiderivative like it did in the previous integration. And when we substitute 2 here, we're going to get a 2 times a 4. And of course here, 2 to the 4th power is 16, which we can just write as 4 times 4. The 4 is absorbed, and we're just left with 8 minus 4, which is 4. So the volume of this solid is 4 cubic units. Now, for those of you that like pictures, the cylinder is parabolic, so it has this shape, but since the region is triangular, it looks like part of a gumdrop. So when we look at this triangular region here, R, and we see that that is the so-called lower bound, and the upper bound is just the non-negative function, f of xy equal 4 minus y squared. So this gives you a nice rendering of the actual solid for which we computed the volume. And we are done.